Now, let us try to determine the electric field of a point charge. Let's assume that our source charge is a positive point charge Q, and we're interested to determine the electric field some r distance away at point P. In order to do this, we will choose a positive test charge Q0 and place it at the point of interest. Since both of these charges are like charges, our source will repel the test charge Q0 in radially outward direction. With a Coulomb force of F sub c. Now we know that the electric field that it generates at this point, at the point of interest, should be in the same direction with the Coulomb force. In other words, it has to be radially outward direction. The magnitude of this force is, from Coulomb's law, 1 over 4 pi epsilon 0 times the product of the magnitude of the charges, Q0, over r square. If we'd like to express this in vector form, then we can introduce a unit vector in radial direction, denoted as r unit, and multiply the magnitude of this force by that unit vector r. From the definition of electric field, we have electric field is equal to Coulomb force per unit charge, in this case per unit test charge. Substituting the explicit value of Coulomb force, we will have 1 over 4 pi epsilon 0 Q0 over r square times r unit divided by Q0. Q0s at the numerator and denominator will cancel, leaving us electric field of a point charge is equal to 1 over 4 pi epsilon 0 charge divided by the square of the distance to the point of interest. Therefore, if we are interested with the electric field generated by a point charge Q some r distance away from the charge at a point P, that electric field is going to be in radially outward direction, and its magnitude is going to be equal to Coulomb constant times magnitude of the charge Q divided by the square of the distance to the point of interest. R is the distance between the source charge and point of interest. The expression over here in the box is also sometimes known as Coulomb's law, in terms of electric field. Now, if we have more than one point charges in our system, and if we're interested with the net electric field at a specific point for more than 1 point charges, then simply we calculate the electric field due to each one of these charges at the point of interest and then add these electric field vectors vectorially to be able to get the total electric field. Therefore, E total, or the net electric field at the point of interest, will be the vector sum of the electric fields generated by each individual charge at the point of interest. Following example is going to be related to the superposition of the electric field vectors.